10, which is one of the organic chemistry. So this part is organic chemistry, haloalkane and haloarene compounds. Well, in this chapter, there will be a combination of two different chapters or two different topics. One is stereoisomerism and another is halides. So first of all, we will deal with isomerisms and isomers. How many types of isomers are available? Well, if you classify isomers, then there are mainly two types of isomers. One is structural isomers, in which molecular formula will be same, but structural formula are different. And another is stereoisomers, in which molecular formula and structural formula will be same, but spatial arrangement of atoms will be different. So, stereoisomers differ in their arrangement in the space, otherwise they are same. First of all, we will see structural isomers. There are mainly 5 types of structural isomers. One, which is known as chain isomer or skeletal isomer. When you take normal, iso and neo of any compounds, they are known as chain isomers. For example, normal pentane, isopentane, neopentane, or normal propyl chloride, isopropyl chloride, neopropyl chloride, normal propyl chloride, isopropyl chloride, or normal butyl chloride, isobutyl chloride, neobutyl chloride. These are all chain isomers. The chain isomers having different number of carbon in chain, and they have some branches, but total number of carbon remain same. Position isomers. Position isomerism appear when functional group is present along with alkyl group. And if the position of functional group is different, then they are known as position isomers. For example, 1-pentanol, 2-pentanol, 3-pentanol, in which position of OH group is different, so they are called position isomers. Next is functional group isomerism, in which molecular formula will be same, structural formula will be different, and they have different arrangement of atoms, so that functional group will be different. This isomerism is possible if two different compounds share the same formula. For example, alcohol and ether. Alcohol and ether are having common formula CnH2n plus 2O. Therefore, they are functional group isomers. Aldehyde and ketone also have the same molecular formula. They are known as functional group isomers. Even acid and ester are functional group isomers. Next is metamers. Metamers having same molecular formula, same functional group, only number of carbons present in alkyl chain are different. So they are called metamers. For example, ether. In ether, if you take these two compounds, diethyl ether and methyl propyl ether, in ether, molecular formula will be same, functional group will be same, but number of carbon present in alkyl chains are different. So they are known as metamers. Ketone, C2H5CO, C2H5, methyl CO, C3H7. So here you can see functional group is same, molecular formula is also same, but number of carbon atoms present in alkyl chains are different. So number of carbon atoms present in alkyl chains are different, so they are called metamers. Some metamers can be position isomers also. How? This diethyl ketone is also known as pentane-3-one, and this is methyl propyl ketone, which is known as pentane-2-one. So here position of ketonic group is on second carbon as well as on third carbon, so they can be considered as position isomers also. Metamerism appear when functional group can be in the center, like ether, ketone, ester, secondary amines, etc. Fifth structural isomer is dynamic isomers or tautomers. In dynamic isomerism, they are also known as tautomers. And tautomerism appear tautomers. Suppose we take this functional group which is having carbonyl group, and in carbonyl group oxygen is partly negative and carbon is partly positive. If you put hydrogen over here, then it is aldehyde. If you put carbon over here, then it is ketone. So carbonyl compounds are aldehyde or ketones. A carbon next to CO group is known as alpha carbon. So this is alpha carbon. Because of inductive effect of oxygen, this carbon of carbonyl group is positive, and therefore the bonding electron pair between carbon of carbonyl and alpha carbon will be shifting towards carbon of carbonyl, and therefore alpha carbon carry positive charge. Electronegativity of hydrogen is already less than carbon, and here carbon is positive. So carbon has more affinity for bonding electron pair of CH. So finally the hydrogen on alpha carbon carry positive charge, and such hydrogen is acidic hydrogen. So if this hydrogen, any one of this, either this or this, if this positive hydrogen will shift to oxygen of carbonyl group, then it will go without electron. So this bonding electron of CH will shift between carbon-carbon, and lone pair over here, pi bond electron between carbon and oxygen will shift to oxygen, and therefore we will get a new molecule in which carbon and carbon will be having double bond, and because of transfer of hydrogen from alpha carbon to oxygen, OH group appear on that carbon, and oxygen has two lone pair of electrons. So this kind of compound is produced from carbonyl group, and here there are two functional groups. A double bond is alkene, and OH group means alcohol. So we take in of alkene and all of alcohol, and we call it enol. Carbonyl group can be considered as keto group. Then this kind of transformation is known as keto-enol tautomerism. Keto-enol tautomerism. So this keto-enol tautomerism produce different types of functional groups without changing molecular formula. But they have different structural formula, therefore they are one of the structural isomers. And they are interconvertible. Enol can be converted to keto, keto can be converted to enol. For example, CH3COCH3 is known as acetone. Now, if you take enolic form of acetone, then hydrogen from either CH3 transfer to oxygen, and we can have double bond between carbon-carbon and OH group. So this is enolic form of, and you can find out number of sigma bonds and pi bonds present in enolic form of acetone. So this is known as keto-enol tautomerism. It is one of the important structural isomer. It is one of the important structural isomers. And here, as these two are interconvertible, this type of isomerism is also known as dynamic isomerism. So, tautomers. These dynamic isomers are structural isomers. Now we will see stereoisomers, in which molecular formula will be same, but even structural formula will be same, but arrangement of atoms in space will be different. There are two types of stereoisomers. First is conformers or tautomers, and second is configurational isomers. First of all, we will discuss conformers or tautomers. So, conformers. Or tautomers. This is possible in alkane when it is for saturated compounds. They are interconvertible. For example, let us take ethane. We write structural formula ethane like this, but this is wrong. In fact, in ethane, each carbon is sp3 hybridized, and therefore structure of each carbon is tetrahedral. So we can write like this. This is CH3, this is CH3. Now when we combine two CH3, we will get ethane. So this is the structural formula of ethane. In ethane, if you take one carbon, this carbon attached to one carbon and three hydrogen. Therefore, it is tetrahedral, and all angles are 109 degree 28 minutes. Second carbon, this one. This is also attached to 3 hydrogen and 1 carbon, sp3 hybridization. All angles are 109 degree 28 minutes. Therefore, both carbons are sp3 hybridized and it is tetrahedral. So we can draw the structure of ethane like this. The same molecule, if you look at this direction, from this direction, then it looks different. Okay? And if you want to draw this, it's very simple. We can draw like this. This one. Or this way. And here you have three-dimensional view of this. And it is known as Sohor's projection. So this is called Sohor's projection. Now the same thing, if you watch it from this direction, front, then you can see only CH3, and the CH3 on the back sides are hiding this one. So the second figure of the same molecule is like this. We can change the color to show that the carbon on the back side It's like this. And this is known as Newman Projection. It is one of the conformer. The bond length of carbon-carbon is 154 picometer. So these two carbons are very close. And these two hydrogens, which are on adjacent carbon, will be in the same line. And there are chances of steric hindrance. So these two hydrogen produce steric hindrance. And due to steric hindrance, they don't like each other. So there will be repulsion between them. Now, how to avoid this interaction? We have to shift the hydrogen from each other without changing structure. So how? There is single bond between carbon-carbon. So, if you give rotation on bond axis, this is called bond axis, and on this bond axis, if you give rotation of 60 degree, then they will go away from each other. Now you can see all hydrogens are away from each other because we have given rotation of 60 degree. Okay? So this we can show it like this. If you give 60 degree rotation, then we will get a new projection. Let this be as it is, but here the position of these three hydrogens will be different than this one, and this is obtained by giving 60 degree rotation. Okay, here also we can give 60 degree rotation, and it looks like this. You can rotate any one of these, doesn't matter. So second carbon as it is, but now hydrogens are going away from this one. So we have two possible arrangements of ethane in space. So the first one is known as eclipse, and the second one is called staggered. In eclipse there will be steric hindrance. In staggered there is no steric hindrance. Therefore, stability of staggered will be more than eclipse. So staggered is more stable than eclipse. So these are conformers or rotamers. We can have rotamers in other than ethane also, like we can have rotamers in butane also. So in butane there will be more than this. Suppose we take butane, CH3, CH2, CH2, CH3. Considering these two carbon is a central carbon, then we can draw Newman projection of this like this. There will be CH3 over here and two hydrogen with this carbon. We are concentrating these two carbons. So here this CH2 and this carbon has CH3, which is over here. Now we change the color for the other one. Suppose this is CH2, this carbon, which is the same over here. It has one CH3 over here and two hydrogens. Oh, okay, like this. So the first isomer is eclipse. These two are methyl groups. These two are hydrogen. Then you can see the first group is like this, where there will be more interaction between two methyl group, and so it is eclipse. Now we will give 60 degree rotation to this. You will say, why 60 degree? The reason is, if you take a two-dimensional view of this, then it looks like triangle. And in triangle, this is the central part. Okay? So what angle should be this? 120 degree. That is why we give 60 degree rotation. So when we give 60 degree rotation to one of these, we will have this type of arrangement. Here you can see both methyl group. They are little far from each other, and this is comparatively more stable than eclipse. This stage is known as gauge. So we will draw gauge by giving 60 degree rotation. So 60 degree rotation gives, let red be the same, and we'll change the position of blue. You can rotate either clockwise or anti-clockwise, doesn't matter. So suppose we give clockwise rotation, then CH3 comes over here, down hydrogen, and here also hydrogen. This is known as gauge. It is comparatively more stable than eclipse. So this is gauge. Now we will give one more time 60 degree rotation. So it looks like this. That means now methyl and hydrogens are coming in the same line. Hydrogen, methyl, and hydrogen, hydrogen. This is known as partly eclipse. Carbon. Now methyl groups transfer over here. On the back side of this, hydrogen, and here also hydrogen. This is known as partly eclipse. Once again give 60 degree rotation. Here. Now when we give 60 degree rotation once again, then you can see both methyl groups are away from each other. All atoms are away from each other. So this is most stable arrangement. Now we will bring the methyl group from here to 60 degree. So it will go down. Hydrogen, and here also hydrogen. And you can see both methyl are away from each other. This is most stable, and it is known as stagger. So staggered is most stable, eclipse is most unstable. So there are 4 types of conformers in butane. Okay. Similarly, we can have conformers in cyclohexane also, which is C6H12. Practically, we draw structure of cyclohexane like this. Hexagon. And which is not possible. And the reason is, each carbon on this hexagon attached to 2 hydrogen and 2 carbon. So each carbon is sp3 hybridized. And in this case, the angle should be CCC or CCH or HCH. Angle should be 109 degree 28 minutes. But here the angle is 120 degree. So when angle is different than 109 degree 28 minutes, you will experience angle strain. And due to angle strain, the arrangement of cyclohexane is changed. And we can have new arrangement of cyclohexane which looks like this. With each carbon there will be 2 hydrogen, and that you can arrange like this. This is known as boat form of cyclohexane. Even boat form is unstable because there will be steric hindrance between these two. And so that transformation takes place, this group will move down and we have a new arrangement like this. It's like this. And this is known as chair form. Well, chair form is more stable than boat form. One of these hydrogen which remain on the axis is known as axial hydrogen. And this hydrogen which is away from axis is called equatorial hydrogen. So, cyclohexane have 2 conformers, boat form, chair form, and chair form is more stable than boat form. So this is all about conformers. Now, the next isomers, which are stereoisomers, are configurational isomers. And there are 2 types of configurational isomers. One, geometrical isomers, another, optical isomers. Configurational isomers are non-convertible isomers. These are non-convertible isomers. So, non-convertible isomers means one cannot be converted into other, while conformers were converted into each other. Like eclipse can be converted to staggered, staggered can be converted to eclipse. But in this case, one cannot be converted to another. They are known as configurational isomers. Now, first of all, geometrical isomers.